previous lesson, we started talking about mixed states and introduced a statistical operator or density matrix to describe them. And today, we'll consider and prove the properties of such an operator. Suppose that we have a statistical ensemble of pure states, that is, some physical system, the quantum mechanical state of which is described by a set of elements. Each element of this set consists of two components, the state vector and the corresponding to this vector probability. On the slide, we denoted state vectors as phi1, phi2, and etc. phi-n, and the probabilities as omega1, omega2, and omega-n. We emphasize that the states phi generally do not necessarily form a basis and may even be non-orthogonal to each other, although in most of the tasks that one has to deal with in practice, both of those features are presented. In this regard, we consider the property of the density matrix, which are carried out for the general case. However, we give their proof for the more important for a special one. So, let the state phi1, phi2, etc. to phi-n form an orthonormal basis for some Hilbert space of dimension n. Then the density matrix ρ, which describes the mixed states of the physical system in accordance with its definition, is equal to the sum of the index I, products of omega I and projector on phi I state. The first property, the density matrix ρ is positive definite, or in other words, its spectrum consists of positive real numbers, each of which lies in the range from 0 to 1. So, let's prove the density matrix properties. For the sake of simplicity, we suggest that density matrix ρ is describing the pure state, and so ρ equals to psi ket vector, psi bre vector. For the mixed states, all proofs will be the same, so we just work with the simpler case. Now, let's consider the first property. Let the set of ket vectors Ni. So let's write down the diagonal element of density matrix ρ, ρ I. By definition, it equals to Ni, ρ, Ni. And in accordance to explicit form of density matrix ρ, we can write the expression in the following form: Ni psi Ni. And these two factors are both just complex numbers, so it's a number 1 and this is number 2. So let's just swap it, and we obtain the following: psi Ni modulo squared. And this quantity is always strictly non-negative, so the proof here is ended. The second property, the density matrix ρ is a self-adjoint operator. The proof of this property follows from the definition. To prove the second property of the density matrix, let's again, for the sake of simplicity, set ρ equals just psi multiplied by psi. So ρ is a pure state. And let's take a Hermitian conjugation of the density matrix. So ρ dagger equals ket psi bre psi dagger, and n equals to Hermitian conjugation of the second vector multiplied by the Hermitian conjugate of second vector. And by the definition, it's equals to ket psi bre psi and equals to ρ. So we just proved the second property of density matrix. The third property. The trace of the density matrix row, that is, the sum of its diagonal elements, is equals to 1. Let's prove the third property of density matrix, which is about the fact that the trace of the density matrix row equals to 1. The trace operation is just an addition of all diagonal elements of matrix row. So sum of the I and I row and I. Here an I, state vectors and I, is the basis of the Hilbert space again. This expression we could rewrite as the following. Sum I, re and I, psi, psi, and I. So here again, two factors, and both of the factors are just complex numbers, so the first number and the second number. Let's just swap it one with each other and obtain the following. Psi sum over I and I and I psi. In accordance to completion conditions, this part of the expression equals to 1 because Ni is the full orthonormal basis of the Hilbert space, and we obtain just psi over psi is the scalar product of two psi vectors, and it's of course equals to 1. So here the proof is ended. And finally, the fourth property. The average of the observed value of L in the case when the physical system is in a mixed state is equal to the trace of the product of the density matrix row and the operator L corresponding to this observable. Finally, let's prove the fourth property of the density matrix. Let's consider an arbitrary physical quantity L, and by the definition it equals to trace or row multiplied by Hermitian operator L that corresponds to physical quantity L. And by the definition of a trace operation, we could write down the following. Sum over I and I row L and I. So let's recall the explicit form of density matrix row and write down the following. Sum over I vector and I psi vector psi L and I. Again, just let's swap the factors, and in accordance to the completeness conditions, which we just used in the proof of third property, we obtain the expression psi L psi. So here the proof of fourth property is ended. So we have proved four properties for the density matrix row. In the case when the states phi1, phi2, and etc. to phi n form an orthonormal basis for some Hilbert space of dimension n. However, the specified properties will persist in the general case when the states of phi1, phi2, and etc. to phi n are neither basic nor even orthogonal to each other. Now, let's consider the density matrix rho that describes the pure state psi, which equals to complex coefficient C0 multiplied by the state vector 0 plus complex coefficient C1 multiplied by state vector 1. So, the density matrix rho could be expressed in terms of only one projector on the state psi. And we could rewrite this expression in the following form: C0 the state 0 plus C1 by the state 1. This is just a state psi multiplied by complex conjugation to C0 and the Bray vector 0 plus complex conjugation of the coefficient C1 multiplied by Bray vector 1. This is just Bray vector psi. So, let's again rewrite that equation in form of C0 modulo squared on the projector 0, 0 plus C0 multiplied by complex conjugation to C1 on the projector 0, 1 plus C1 multiplied by complex conjugation to C0 on the projector 1, 0, and the first term is C1 modulo squared on the projector 1, 1. We could write it down as in a matrix form, so rho equals to C0 modulo squared, and here the second diagonal element is C1 modulo squared. And there are two non-diagonal elements, C0 complex conjugation to C1 and C1 complex conjugation to C0. And here the non-diagonal elements of the density matrix are complex numbers, and they could be compared with the projectors from the state 1 to state 0. Here, projector 1 to 0, and to the projector from 0 to 1. This projector defines the physical transitions from the corresponding states. And the diagonal elements obeys the normalization condition, and we could write the following: C0 modulo squared plus C1 modulo squared equals to 1. In conclusion, we know that if a closed quantum system is in a mixed state and is described by a density matrix rho, then its evolution is described using the quantum Liouville equation or von Neumann equation. The time derivative of the density matrix rho sub 0 multiplied by the imaginary unit and the reduced Planck constant with a line equal to the commutator of the Hamiltonian operator of this system and the density matrix rho 0. That's all for now. Thanks for your attention.